we had ended talking about SN1 and introducing the idea of E1. What we now want to talk about is the interrelatedness of SN1 and E1. And since SN1 and E1 reactions share the same first step, if we do a reaction where we get an SN1 product, we're also going to get an E1 product. And so in homework problems or on an exam, I will usually write the instructions as if the reaction is SN1 and E1, write the SN1 product in the major, well, actually I say write both E1 products and then indicate which one is major. So let's say that we were going to do this reaction. The first question is, what is the mechanism for this reaction? Well, if I look at this, this is a tertiary halide plus a weak nucleophile. Weak nucleophiles are neutral nucleophiles like this alcohol. It can only react with a carbocation, and so therefore it's going to react with this tertiary halide. So this is not only going to be an SN1 reaction, but now it's also going to have an E1 component since those two mechanisms share the same first step. So we're going to write the SN1 product mechanism, and then we're going to write the mechanism to form both of the products and indicate which of the major E1, which one is the major E1 product. So let's start with the first step in an SN1E1, and that is to break the carbon-chlorine bond to make a carbocation. So we'll go through the transition state then. We'll be breaking the carbon-chlorine bond to then form the tertiary carbocation and Cl-. So we've indicated that the carbon-chlorine bond is breaking. This carbon is going from 0 to +1. So in the transition state, it is delta plus. The chlorine is going from 0 to -1, so it is delta minus. So that's a transition state. Now, in this carbocation, let's write the SN1 mechanism. And so the SN1 mechanism would be to take this methanol molecule and have it take its pair of electrons and add it to the carbocation. So in terms of, again, our transition state, we're going to form a carbon-oxygen bond. The oxygen loses the lone pair, that's forming the bond. So it will, that's the bond that's forming in the transition state, and then the final product will be that oxonium ion. In terms of the charges here, the positive charge is going from the carbon to the oxygen in that transition state. Okay, and once we form the oxonium ion, it would like to lose this H plus to form the substitution product, so the OH bond will break and the pair of electrons will go to the oxygen. In terms of that transition state, in this case, what we could do is we could basically say the chloride is what's going to catch the H plus as it leaves. And so in terms of the transition state for this product, we'll write the transition state down here. We would have our oxygen-hydrogen bond breaking, our hydrogen-chlorine bond forming, and then our CH3 group attached over here. The final product for this reaction is going to look like this. It's going to have an OCH3 group there, and I'm going to put the OCH3 group, I'm going to put the CH3 group where it was before. The oxygen will have its lone pair, lone pair restored, and then in terms of we'll get HCl formed. So in terms of this transition state, putting in the charges, we'll have the chlorine going from negative to 0, so delta minus, and this oxygen going from +1 to 0. And so that would be the complete mechanism for the SN1 reaction. However, there is an E2 portion of this mechanism. And the E2 portion of this mechanism I'll go ahead and write up here. So I'm going to start with the start with the carbocation. Now, the carbocation is our alpha carbon, and we have 3 beta carbons in this case attached. And we have to make sure that there are hydrogens attached to those beta carbons, because those are the beta hydrogens that would be lost. Now, hopefully you see that if we lose either of these 2 hydrogens, that we'll end up with the same alkene product. So let's call those beta hydrogen A's. And then down here, this is a different beta hydrogen, which will give us a double bond in the middle of the molecule. So what will happen if we want to take our chloride again? We would say the Cl minus is going to come in, catch the hydrogen as it takes its pair of electrons and forms the double bond. So in terms of the transition state for that, we are breaking the carbon-hydrogen bond, we are forming the carbon-chlorine bond, and we are also forming the double bond. So that's our transition state. The final product then will have the double bond in that position plus HCl. So in terms of charges, the chlorine again is going from -1 to 0. This carbon is going from +1 to 0, so it would have a delta plus charge on it. And so that would be the transition state for losing beta hydrogen A to give us the final product. If I wanted to lose beta hydrogen B, my chloride would come in and catch the HB as it takes its pair of electrons and forms the double bond. So over here, that transition state would look like this. We would be breaking that carbon-hydrogen bond, forming the hydrogen-chlorine bond. We would have a delta plus charge on the carbon as it goes from +1 to 0, and the chlorine would be delta minus. And so there's our transition state to get us to our final product, which now is going to have the double bond there. So let's call this product B simply because it came from beta hydrogen B, and let's call this product A, E1 product A, for that reaction. And so my question when the video stops is, which is the major product of this reaction? A, B, or equally A and B? Okay, so go ahead and go ahead and answer that question when the video stops. Okay, which product is the more stable product? It is the one that is the most substituted, the most stable. That's the major product of the reaction. How many alkyl groups are attached to product B? Well, we would have 1 hydrogen attached here, which means we have 1, 2, 3 alkyl groups. So we've got 3 alkyl groups there. Over on product A, how many alkyl groups do we have? If we put in our 2 hydrogens there, we just have 2 alkyl groups there and there. So which one is more substituted? The more substituted product is B. That means it is the more stable product, and therefore B is the major product of the reaction. Okay, so if I'm asking you to write the mechanism, I will tell you which product I would like you to write the mechanism for, or I might say write the mechanism for the SN1 reaction and for forming the major product of E1. So we're going to need to know that the more substituted alkene is the major product. If I'm just asking you to write the products, then I will say if it's an SN1 and E1 reaction, write the SN1 product. identify the possible E1 products and indicate which one is major. So that's what we've done in this mechanism. Okay, so the whole idea here is that SN1 and E1 reactions, since they share the same first step, both products are going to be formed in the reaction. So then the next logical question is, could we favor SN1 over E1 or E1 over SN1? And what kind of factors would go into that? And that's a good question. The easiest way to answer that would be to say, if you want E1, then make sure you have no nucleophile in the reaction mixture, right? Because if there's a nucleophile, it'll undergo SN1. But how realistic is that? And to be honest, the only way that's realistic is if you just took the alkyl halide by itself and heated it and decomposed it to form HCl and the double bond. So that's not really a realistic position. So we're always going to get a mixture of SN1 and E1. Now, one way to favor E1 over SN1 is to basically use heat. And if you use heat, then you tend to favor the alkene product. So that's one way to favor E1 over SN1. But the simple fact of the matter is, you're probably going to have a nucleophile present. And remember that if this is an SN1 mechanism, or even an E1 mechanism, that the nucleophile strength doesn't change the rate of reaction. And if you're saying, well, I don't remember that. Remember, SN1 or E1 has the same first rate determining step. What was the rate determining step? Breaking the carbon-chlorine bond to form the carbocation and the chloride. In an SN2 mechanism, what happens? The carbocation reacts with the nucleophile. In an E1 reaction, what happens? The carbocation basically loses an H plus to give you the carbon-carbon double bond. In either of those cases, this is the slow step. So it doesn't matter how strong the nucleophile is, it doesn't play a role in the rate. So using a stronger nucleophile isn't going to favor SN1. Using no nucleophile would favor E1, but again, that's just not realistic. So in general, what we say is we use heat in order to try and form more alkene product. We'll talk about that a little bit later with alcohols. Okay, so can we favor SN1 over E1? Not really. We're going to get both of the products formed. What about carbocation rearrangements? Are they possible in these SN1 and E1 mechanisms? Of course they are. So if I take my carbon-chlorine bond and I break that, and I'm just going to go straight away to the carbocation intermediate, I would get that carbocation intermediate. So in this case, could this undergo carbocation rearrangement? Well, let's look at the carbons attached to the carbocation. Do they have hydrogens? Notice that if you're saying, well, that's a beta hydrogen, yes, it is. This is an alpha, beta, and beta carbon, and so the beta hydrogens are the ones that can undergo 1,2 hydride shifts. So if I took this hydrogen and I shifted it and I did a 1,2 hydride shift, would I get a more stable carbocation? And the answer is yes. I would get now a tertiary carbocation. So I went from a secondary carbocation to a tertiary. So are carbocation rearrangements possible? Yes. And so now what would happen? Well, if this was water, in the SN1 mechanism, the water would come in, add to the carbocation, we would end up with our oxonium ion, and then the Cl minus would come in and take the H plus as the OH bond breaks, so that I would form now the OH group there. The hydrogen that shifted would be there. I'll show it here. That's the hydrogen that underwent the shift. And I would also end up with HCl. So in this case, this would be the SN1 product with a carbocation rearrangement. I'm just going to talk about the transition state for the shift step, just so that we can remember what that transition state looks like. So in that transition state, the hydrogen is partially bonded to each of the two carbons, the one it's shifting from and the one it's shifting to. And so the delta positive charge then is spread over both of those carbons. And so it's on its way from being a secondary carbocation to being a tertiary carbocation. So this would be the transition state for the hydride shift. So what would happen in the case of the E1 mechanism with the carbocation rearrangement? Well, same thing. Same first step, lose the chloride. Same second step, shift the hydrogen to form the more stable tertiary carbocation. And then once I had the more stable tertiary carbocation, what would I end up with? I would end up with this tertiary carbocation. Notice that the alpha carbon basically has now shifted. So for the elimination reaction, this is now the alpha carbon. We have a beta carbon here, we have a beta carbon here, and now we have a beta carbon there. Do they have hydrogens? The answer is yes, they do. Again, if you notice that losing this hydrogen and losing this hydrogen, as losing those as H plus would give you the double bond inside the ring and exactly the same product. Whereas losing this hydrogen outside the ring would give the double bond to the ring, which is a new product. So now, in terms of writing the two possible products, we would again do the same thing. Our chloride, as this pair of electrons moves to form the double bond, the chloride comes in and grabs the H plus. So now we have the double bond in that position plus HCl. And if the HA, we break the carbon HA bond and move that pair of electrons to form the double bond, the chloride could come in and grab HA. Plus HCl. So now we have product A. No, that would be product B. If I'm using HA and HB, this would be product B. This would be product A. So my next question is, when the video stops, what is the major product of this reaction? Your choices are A, B, or A and B equally. So go ahead and answer that question, and then we'll see if you're right. Okay? As you come back, how many hydrogens are attached to this double bond? Just one. How many hydrogens up here are attached to this double bond? Just one. What does that mean? That means there's 1, 2, 3 alkyl groups attached to that double bond. There is 1, 2, 3 double bonds attached to that one, they have an equal number of double bonds, which means they have, and I'm not going to say the same stability because that's not completely correct, but what I'm going to say is they have equal stability. And so therefore A and B are both the major products of the reaction. Okay, so that's how we would look at a carbocation rearrangement. Again, after you lose the leaving group, you form the carbocation, do a hydride or a methyl shift, and once you reset the carbocation in its new position, that gives you a new alpha and a new set of beta carbons to write the double bond with. So are carbocation rearrangements possible? Yes. But it's very similar to what we did when we did carbocation rearrangements before. For an E1 mechanism, it's just simply now I have a new carbocation with a new set of beta carbons and beta hydrogens. Okay. Okay, so now let's change the viewpoint a little bit. Let's change the leaving group. And when Zaitsev determined his rule that said the most stable product, the most stable alkene was the major product of the E1 mechanism. We borrow what he did to call it the Zaitsev's rule. So Zaitsev's rule says when you do an elimination reaction by an E1 mechanism, you get the most stable product. Well, what Zaitsev did was he actually did dehydration reactions of alcohols. And when he did a bunch of those, what he found was that he always got as the major product the molecule with the most substituted double bond. And so his rule specifically was you get the more substituted alkene in basically a dehydration reaction. Well, so he didn't do alkyl halides, he reacted to alcohols. We have multiple issues here. Number one issue is the OH group is a poor leaving group. This is a very poor leaving group. Why? If you're screaming at the computer because the OH minus is a strong base, you're correct. Remember, leaving group ability is based on one thing, basicity inversely. So hydroxide is a fairly strong base, which means it would be a very poor leaving group. Hydroxide will just not leave on its own. So how do I make hydroxide leave? Well, let's use H+, which is an acid. So you might say, well, what's going to happen when an alcohol is reacted with acid? The acid is the electrophile, the oxygen of the OH group is the nucleophile, and so what's going to happen? I'm going to protonate my OH. So I'm going to form my OH bond. Right? That would be my transition state of forming the OH bond. And then having now two hydrogens attached to the oxygen, which would now have a positive 1 charge. If you're saying, boy, that looks familiar, It is. It's the reverse of when we lost our H plus to give us our oxonium, or to give us our alcohol. Now I'm just reversing it. I'm taking the alcohol and I'm adding an H plus to it. In terms of this transition state, what's happening? Well, the H is on its way from being positive to neutral. The oxygen's on its way from being neutral to positive. So that's where the partial charges would go, and now I get the oxonium ion. Now, if the oxonium ion, if this group right here was to leave, and if it was to leave, then what I would have happen is I would have this pair of electrons in the carbon-oxygen bond be given to the oxygen. We would have a partial bond between the carbon and the oxygen. And once the entire molecule leaves, I end up with a carbocation. But what else do I end up with? Water. So what was the leaving group in this process? And before we answer that question, let's go ahead and write the transition state. Carbon going from 0 to +1, that means there's a delta plus on this carbon. And oxygen going from +1 to 0, there's a delta plus charge there. Have we written that positive? Have we written a transition state that looks like this before? Yes, because the water adding to the carbocation is exactly the same transition state you get as when water leaves to form a carbocation. Okay, see the interrelate. Hopefully you're kind of seeing the interrelatedness of this. So now what I'm doing is a lot of the reverse of what I just did in the previous SN1 reactions. So what did I do? I converted a terrible leaving group in hydroxide into a much better leaving group, water. Well, which one is the weaker base? Water. What is it about leaving group? Leaving group abilities based inversely on basicity. The weaker base should be a better leaving group. So turn the OH group that won't leave into a water molecule that will. And this is what Zaitsev did. Now I have my carbocation, and now I'm stuck. And I'll tell you why I'm stuck. Because now that I have the carbocation, I have to think about, am I going to get an SN1 reaction? Am I going to get an E1 reaction? If I'm going to get an E1 reaction, what's the major product of the reaction going to be? Well, we can figure that out. But let's just contemplate this idea of I've got a carbocation. So my big question here is, what H plus do I use? And you're like, what are you talking about? Okay, I just can't go down to the stock room and grab a bottle that says H plus. There's got to be something that it comes from. So what's the source of my H plus? Is it HCl? Is it HBr? Is it HI? Well, what's the problem with using those three? The problem with using those three, and it might not be a problem, is what do I have now? Let's say I use HCl to do this reaction. So now I come back up here and I go, oh, that's right. The Cl was giving up its H plus to protonate the OH. So down here I'm going to have a Cl minus. And then I'm going to lose the water and now get a carbocation. What's left over? My Cl minus. What's that Cl minus going to do to that carbocation? It's going to add. And then what am I going to get? Now I'm going to get an SN1 mechanism. So now what I'm going to end up with is I'm going to end up with a carbon-chlorine partial bond, a delta minus on the chlorine, a delta positive on the carbon. And my final product. So what would this mechanism be? I would consider this to be an SN1 reaction. Why? Substituting OH with a Cl, that's substitution. They're both nucleophiles. Did this undergo a carbocation intermediate? Yes. And that's the way we're going to define 1 now. 1 means carbocation intermediate. 2 means no carbocation intermediate. And we'll drill that later on. So if I use one of these HX acids, then what happens? I get an SN1 product. That's great. That's a great reaction because now I can substitute an OH, which again, terrible leaving group, with a halogen. But if I just tried to say, oh, well, let me take this alcohol and react it with Cl minus, what's going to happen? OH is not a good leaving group, and so you're going to get no reaction. But if I put H plus in here as HCl, what happens? I get my SN1 mechanism. Okay? So if you want to do SN1, you can use an HX acid and substitute for the OH group after the water leaves. Okay, that sounds somewhat reasonable, except I've got a couple of issues here that I need to deal with. What I've written now is an SN1 mechanism where I go through a carbocation. So after I take my OH and I protonate it, and I lose my water to form a carbocation over here, then I can add the halogen. I guess my first question would be, could I do this with a primary alcohol? So could I do this reaction by SN2? And the answer would be, sure, I could do that. I'm going to skip ahead here and actually pull up a molecule where there is a primary OH group. So could I react this alcohol with HCl in an SN2 mechanism? Now the 2 means no carbocation intermediate. And so I'm broadening the definition here of SN2. So let's sort of write a mechanism here of what would happen. I would take my OH group with my lone pair, and I'm going to add to it my H plus Cl minus. The oxygen is going to basically, the pair of electrons is going to be used to grab the H plus. The pair of electrons will go to the chloride. So what will I end up with? I will end up with the oxonium ion, and I will end up with a Cl minus. Okay. Now, can this water leave? It better not, because this is a primary carbon that the leaving group is attached to. So water will not leave. But what about the chloride? Could the chloride wrap itself around, come in here, and kick the water off? Yes, it could. Now, I'm going to need some heat for this reaction. So I'm going to end up with an SN2 transition state. This reaction is now going to go by SN2. So all SN2 reactions look like this. They have a trigonal bipyramidal carbon with the leaving group on one side and the nucleophile on the other. And now this is a CH2 group, so that means one hydrogen, and a CH2 with a ring on it. So here's my transition state. And the heat's required in order to fully kick off the water molecule. It's a better leaving group, and so if I apply heat, the chlorine will actually be able to kick it off. Okay, now I have a couple of questions. Question number one is, what is the charge on this chlorine? Is it a delta positive or is it a delta negative? So go ahead and when the video stops, choose your answer. Is that chloride going to be delta minus or delta positive in the transition state? Okay, next question. What is the charge on that oxygen in the transition state? Is it delta plus or is it delta minus? So when the video stops, go ahead and write or choose what charge it is, delta plus or delta minus. Okay. So in this case, let's write the final product so that if you're averaging your charges, you can figure out what the product is. So in this case, what I'm going to have is the CH2 group attached to the cyclohexane ring, and then another CH2 group, but now with the chlorine attached to it. What was my leaving group? My leaving group was water. So now let's figure out what the charge in the transition state was. The charge in the transition state was this oxygen is going from +1 to 0. That means the oxygen is delta positive. The chlorine is going from -1 to 0. That means the chlorine is delta minus. Okay. And now you're looking at this going, but wait, I thought all SN2 transition states had a delta minus and a delta minus. We've now broadened our examples of SN2 transition states and SN2 reactions. So in this case, the oxygen is basically going from being positively charged to now being neutral. Okay. So my point, what is my point? That's a question that we should constantly ask. We should constantly ask ourselves, and I should constantly ask myself, what is my point? My point is that, number one, if I want to substitute this OH group with a halogen, I need to use HX. If it's a primary system, it's going to undergo an SN2 reaction. If it's like the last one, if it's like the last one, where it was a secondary system to start with, then once I protonate the OH and make the water, it can leave and form the carbocation, and that's what it will do. So we can do substitution with HX on an alcohol by either SN1 or SN2. And the SN1 mechanism would be when I had a secondary or if I had a tertiary alkyl halide. The SN2 mechanism would happen when I had a primary system. Okay, so I can do either one. Right? Okay, now this slide didn't say anything about SN1 and SN2 mechanisms, did it? No, because what I'm trying to do is to show you, if I'm trying to do E1 and I chose HCl, I failed. So this is one source of H+. So I want to do E1 now. Or in a primary system, I want to do an E2. Can't choose HX. I can't choose HCl, HBr, or HI. So what do I choose? Well, I need to choose an H plus source that has a weak conjugate base. And if you're saying, well, wait, halogens are weak conjugate bases, yep, you got me. So what do I mean by a weak conjugate base? I also mean that it is a very, very poor nucleophile. That's a little different. So how do we make a poor nucleophile? You say, but we would make a weak conjugate base. Okay, so let's take a little diversion here. This is your standard equilibrium for acids. HA dissociating into H plus and A minus. And if you're like, but what about the H3O plus? Okay, the H3O plus is there if I throw in water and I combine the H plus with the water. Just let's do something simple here. How do I make an acid stronger? How do I push this equilibrium to the right and make HA more acidic? Make HA a stronger acid. How do I do that? Well, how did you push equilibriums in general chemistry? If you said Le Chatelier's principle, great. That's what you did in general chemistry. It ain't going to work here. You might say, why not? Because there's nothing over here that I can use an excess reagent to push the equilibrium. We'll remove one of the two products. Well, yeah, that's not really going to work all that well. So let me introduce a new way to push the equilibrium to the right. I can push this equilibrium. Oh, you know what? If this wasn't an equilibrium, if this was a reaction, how would I make this reaction go faster? I would invoke my friend the Hammond's postulate. And I might say, you know what? If I make this A minus more stable, wouldn't that make the reaction go faster? And the answer is yes, it would. But what effect does making the product more stable have on an equilibrium? It's the same. So if we make the conjugate base more stable, then we'll go ahead and push the equilibrium to the right. Good concept, right? That's a good concept. How do we apply that? Well, here's an acid you learned about in general chemistry, H2SO4. Here's another acid you learned about in general chemistry, H3PO4. Let's use H2SO4 as our example. So when H2SO4 dissociates, it forms H plus and HSO4 minus. Is HSO4 minus very stable? I don't know. Let's write out its Lewis dot structure. What makes the HSO4 minus ion very stable? What does it have a lot of? If you said it has resonance structures, you would be correct. It has resonance structures, right? You take this pair of electrons, move it here, move that pair of electrons there, or we could even move this pair of electrons out here. So it has lots of resonance structures. Back when we started organic chemistry, what did we say? The more resonance structures you can draw, the more stable the molecule. So something like HSO4 minus is very stable because it has a lot of resonance structures. Now, let me ask another question then. What kind of base would it be? Well, HSO4 really completely dissociates in water, so this is going to be a very weak base. If it's a weak base, what kind of nucleophile will it be? Okay, so now we're going to go into the real world and go out of my little nice, uncomplicated world where a negatively charged nucleophile was strong. That's not always the case. In this case, HSO4 minus is a very, very weak nucleophile. Why? Because it's very stable. It's a very weak base. Also, people have proposed that said, well, it's kind of sterically hindered. Okay, if it supports my argument, I'll give it to you. So either way you look at it, HSO4 minus, or over here with H3PO4, same kind of equilibrium, H plus and H2PO4 minus, either one of those would be a great acid to use if you wanted the conjugate base to be non-nucleophilic. So now if I want to do E1, I have one of two great bases. So now let's do this reaction with H2SO4. And remember a couple of slides ago I said, if you want to favor E1 over SN1, use some heat. So now let's combine both. Let's use H2SO4 and heat to do this reaction. Okay, so now I have my H2SO4, my O of the alcohol is going to grab the H plus, and then the pair of electrons is going to go to the oxygen here. Okay. So in terms of what happens, now what I did was I just protonated my OH group to make an oxonium ion. And now I end up with H right, and that's now HSO4 minus. Why do I have a little s there? So now I have an HSO4 minus. So now what I did was I just protonated my alcohol. So what's going to happen in the next step? I'm going to break my carbon-oxygen bond, and I'm going to go ahead and form the carbocation and water. HSO4 minus, the conjugate base of the acid, sulfuric or even phosphoric acid, I don't have a nucleophile now that can come in and add to the carbocation. So and if I'm applying heat, what I now have is a situation where I'm going to do totally E1. And so now here's my alpha carbon. Here's my beta carbon with my beta hydrogen. Over here is a beta carbon with a beta hydrogen as well. So now what I've done by using H2SO4 or H3PO4 is that I am now in a position where I don't have a nucleophile to do SN1 with. I'm now just going to do E1. And so which hydrogen am I going to lose? Well, this is a new problem, so let's call this HA. Let's call this HB, just to keep you on your toes. Which hydrogen am I going to lose to form the major product, HA or HB? When the video stops, go ahead and tell me which one is going to be lost to form the major product, A, B, or both of them to form the products that are the same stability. Okay. Well, let's now do that reaction. So now let's lose HA. So now I'm going to lose the HA plus, and I'll come back in a minute and sort of change that. So I form the double bond here. If I lose HB plus, where's the double bond going to go? It's going to go there. So we'll call this product A. We'll call this product B. Which one is more substituted? One hydrogen here. Two hydrogens there. Which one's more stable? A is more stable because it's more substituted, and so it would be the major E1 product. Okay? So that's how to force the reaction to go into E1. Use H2SO4 or H3PO4 and heat. And take advantage of the fact that this is non-nucleophilic. Now, you're saying, wait, you haven't been losing just an H plus on its own. And you're correct, because people at other fine institutions have criticized me for teaching that way. And I guess it must still leave a mark because I'm kind of touchy over it. So what would happen in this case? What I would say is this. Our HSO4 minus is going to collect the H plus as it leaves. And down here, the HSO4 minus is going to collect HB as HB leaves. And we'll leave it at that. If you wanted to say, well, wait, isn't there water in here that could also do that? Yes, and actually that would be more correct, but something is going to grab the H plus as it leaves. And so we're going to end up with this, plus in this case, we're going to end up with H2SO4 at the end. Okay. Which brings me to something I need to comment on here. And that's this. That notice I started with H2SO4 and I ended with H2SO4. So now we have to ask ourselves the question, what is the role of H plus in this E1 mechanism? In this what's called dehydration reaction. And I should take two steps back and say, why is this a dehydration reaction? The reason it's a dehydration reaction is because I lost water in this reaction. So I dehydrated the molecule. In essence, to form the major product, what did I do? I lost water. So I dehydrated it. So in terms of what is the exact definition of the role of H plus? Well, it's a catalyst. The role of H plus in this case is as a catalyst. What is a catalyst? A catalyst is something that's used in one step of the mechanism, but it's regenerated in another step of the mechanism, so it doesn't show up overall. H2SO4 started out as a reagent, but ended up as a product, therefore it doesn't show up in the overall reaction. So the H plus from H2SO4 or H3PO4 is a catalyst in this E1 mechanism. Okay. So now we could substitute the OH with HCl, HBr, HI, HF, I suppose. But we can also not just do a pure E1 reaction, a pure dehydration and form only the double bond by changing our acid source to H2SO4. And here's the take-home point if your head hasn't exploded from all this information. We started with the idea of, can I favor SN1 over E1? And what I said here was, probably not. Not with an alkyl halide. All right, great. But if you do want to favor E1 to very high yields, make it an alcohol and use H2SO4 in heat. Easiest way to favor E1. Okay? So that's how we favor E1, is by using sulfuric or phosphoric acid. Right. What about E2? What happens if I take a primary system that can't form a carbocation and react it with sulfuric acid and heat? Then I'm going to get an E2 mechanism. I'm going to regret bringing this up in the next set of lecture videos, but I'm going to do it anyway. What would happen in this case? Well, remember, my new definition of 2 means no carbocation intermediate. So how would this work? So let's say that I took my primary alcohol here and I reacted it with sulfuric acid. All right, so I'm going to have that alcohol OH group react with the H plus and then generate HSO4 minus in that step of the mechanism. So what do I end up with? I end up still protonating my OH group and now making my oxonium ion, and now I have the HSO4 minus as the conjugate base. Now, the fact that this is not a nucleophile means that it won't come back around and kick off the water, even in the presence of heat. It will not do SN2. So then the question is, well, how do you get an E1, or how do you get an E2 mechanism? How do you form the double bond? Okay. The carbon attached to the leaving group is the alpha carbon. The carbon attached to the alpha carbon is the beta carbon. That's just simple Greek lettering. Whenever you have a primary alcohol, you will only have one beta carbon, which means that if there is a beta hydrogen there, that's the hydrogen you will lose in the process. Okay, so this pair of electrons will move here, and the water will leave all in one step. Now, that H is going to be captured by the HSO4 minus. So again, as the H plus is lost, it gets recombined to form H2SO4, and then the pair of electrons moves here and the water leaves all in one step. So I should write the transition state out for this, and we'll talk more about this in an upcoming lecture video, but I'm breaking the carbon-hydrogen bond. I am forming the oxygen-hydrogen bond of the sulfuric acid. I am forming the double bond here to form the carbon-carbon double bond. And I shouldn't have written that as a regular bond. I am breaking the carbon-oxygen bond to form the water. So we worked our way up from 2 dotted lines to 4. And that's what the transition state's going to look like. We'll put in our charges here in a moment. Right? What's the final product going to look like? The final product is going to have the double bond there. I'm going to end up with H2SO4 for catalyst, and I'm also going to end up with water. So in terms of charges, where should the delta minus, delta positive charges go? The oxygen on the H2S on the HSO4 is going to be delta minus. The carbon, there is no delta positive charge on the carbon, which is actually good. The only delta positive charge is on the oxygen as it's going from +1 to 0. So since this mechanism did not involve a carbocation, I call it a 2. Since it formed a double bond, it is an E2. And so when you do a reaction, when you do a dehydration of a primary alcohol, you can get one product. And so you'll get the double bond at the end. Okay. So that's our E2 mechanism for a dehydration reaction. Okay, so what about stereochemistry? And what do you like? Racemic mixture? No, I'm not talking about stereochemistry that way. I'm talking about if I was to do a dehydration reaction with H2SO4 and heat. Now you're looking, oh, what the is that triangle? That triangle is a symbol for heat in organic chemistry. So if I add H2SO4 and heat to this alcohol, could I write the major product of this reaction? Sure. That's the carbon attached to the leaving group, right? The OH is going to be protonated, leave as water, and then I'm going to get my carbocation. I have 2 beta hydrogens, or 2 beta carbons that have beta hydrogens attached to them. Now in this case, you might say, but they're the same, so I'm going to end up basically forming a double bond between the beta carbon and the alpha carbon, and I'm going to end up forming water. And it wouldn't matter whether I formed the double bond between the beta carbon on the left or the beta carbon on the right because it's the same product. Absolutely true. Okay. So we're going to have to become proficient in writing just the major product of the reaction and not going through the mechanism. Although if you're completely lost at this point, let's just sketch out a real quick mechanism, no transition states. So the alcohol grabs the H plus from the sulfuric acid. I end up with my oxonium ion and my HSO4 minus. Since this is a secondary carbon, I can lose water. So I lose my water and I form this. If you're going, wait, okay. Sometimes I will write minus water to get to the carbocation. What I could do, always do is just put the carbocation plus water. So sometimes you'll see minus water over here, or minus H plus. Okay, now I have that carbocation, that's my alpha. Then I've got beta carbon 1, beta carbon 2. Fortunately for us, if we lose the H plus on either side, and again, to write the complete mechanism for this, right? As the H plus is lost, it's going to go back to the HSO4 minus. I'm going to get these two products. Okay, so that's the mechanism to get us here. You'd say, but those are the only two products. Well, actually, they're the same product, right? So there's only one product here. So there's really only one product. Or is there? Those are the two products that are formed. In other words, cis and trans. So that's what I'm talking about with stereochemistry. If you have the possibility of forming cis, trans, or EZ, what are you going to form? And I'm just going to say this. You're going to form the most stable alkene. What do you think that one is here? I'm curious. So when the video stops, tell me, what do you think is the more stable here, cis or trans? Again, this is graded on participation, so if you're like, I don't know, take an educated guess. Cis, trans, or they have equal stability. What do you think?
The one that is more stable is going to be the one that is trans. Why? Because it's all about sterics. What would be more steric hindrance? To have the methyl group and the ethyl group on the same side of the double bond or on opposite sides? Well, having them on the same side is going to cause some steric hindrance, and so that's going to make the cis less stable than the trans, where there is no steric hindrance because the methyl group is basically on the same side as a small group hydrogen. So in this case, when we do a dehydration reaction and we can form either the cis or the trans product, we're going to favor the trans product simply because that's going to alleviate the steric hindrance. Now, if it forms potentially an E or Z, I guess what we're going to try and do is have the combination that has the smaller groups next to each other. And that could be a little complicated, but that in general is what we're going to do. Okay, so that's what we're talking about with the stereochemical preference of this reaction. It's just simply, it's going to form the more stable product. Now we're going to take into account cis and trans in determining that. Okay. Okay, so can these types of E1 reactions, dehydration reactions, involve carbocations? Why would I bring it up if it's not the case? So in this case, if I took this alcohol that we've been working with and I use sulfuric acid and heat, this is one of the products that I could observe. And it would come about from a carbocation rearrangement. So what would be the mechanism of me going from this alcohol to this alkene? And notice that this carbon can only form a double bond to its left and right. This is a double bond in a different place. So guess what it involves? A carbocation rearrangement. So can we write the mechanism of this? Well, let's find out. So this will be an online quiz question where you'll write out the answer and submit it. So write the mechanism to go from this alcohol to this rearranged product using a 1,2 hydride shift of a carbocation rearrangement. Okay, and you can go ahead and do that. Okay, so that's the end of this lecture video, and we will pick it up with more traditional E2 reactions in the next video.